Okay, that's better now. I feel like I can be heard and Tommaso is able to be heard. All right, well, I'm very happy to introduce to you today Professor Tommaso Bellini, a very good friend of mine of many, many years. Tommaso is the professor of applied physics at the University of Milan. He is also a visiting faculty at UC Boulder, where he has been in an academic relationship with that university, coming here regularly over the last 20 years. He's also a founding member of Ulysses, which is an organization that seeks to propose, expound, and let people know about some of the most fascinating things that we discovered in the physical world, and try in some way to derive a deeper and fuller understanding of this world in which we live. This society proposes major events in Italy and in other countries of the world that draw many thousands of people. Today, he is going to speak to us about the eye, about the optical device that sits in our head and the way it communicates to us. But I'll let him introduce the topic rather than me try and say anything about that, because that's precisely the topic that he's going to deal with today. So without further ado, I offer you Professor Tommaso Bellini.
Good morning. It's very interesting to be here with you today. I'm going to present a work that I've done with a group of friends, which are people of the Association Eresis. And this association is an association of people who work in science or in technology. And we are trying to revisit topics that are scientific or technological without keeping very well in front of us the big questions that all of us have about life, about destiny, about meaning. And so, because these big questions of life are not by themselves scientific questions, but a lot of times science is brought by this question. I have some angles that can clarify and help our exploration in life and our understanding of life. Okay? So what I'm going to present today is a work that has been done a few years ago together with this friend. It's a kind of interdisciplinary work. It's not my expertise nor the expertise of the other. Put together, we were expert enough to do it though. And so it was turned into an exhibit that went around in Italy, had many thousand visitors. And also I went around to present this in different occasions in Italy, so it's very interesting to be also here. I actually went a few months ago to my own parish in Milano. This presentation is focused on one particular sense, which is vision, seeing, the experience of seeing. And the reason we started looking among the different topics, we explore many topics, but to this topic is because senses are an interesting factor. It's really the place where our intimate self, gets in contact with the external reality. It's the place by which we know the reality around us. There's this interesting quote from St. Thomas Aquinas that says that nothing can be in our thoughts if it wasn't before in our senses. And you tell me if you cannot hear me, right? Yes. Can you hear me fine? Okay. And in particular, seeing is an important sense. In fact, we even use see to say understand. I see it, right? So this is how important it is for us, and it's also pointing to another factor that I will talk about a little later. So I will ask you to follow me in a short journey where I will tell you the elements that make it possible for us to see. And these elements are from the natural world. These are light, the eye, this special thing which is the retina in the eye, and then what happens, what kind of something is sent to our brain. And it's kind of necessary to go through this journey to reach the point I want to reach at the end. I think there are at least two important conclusions that I would like to share with you that are made stronger if one follows through this path of understanding why do we see. So let me go a little through that. I mean, the first element is light, okay? Light, let me tell you this kind of a little technical thing. Light is a wave, okay? It's a wave like the wave of the sea. The wave of the sea, they bring water. The wave of light are called electromagnetic, and they bring around something which is really difficult to perceive. We have no instinct perception of it, which is the electric field. But it doesn't really matter what it is. We can accept that there are these waves that propagate not on the surface, like in the sea, but through the space. And one important aspect of these waves is the length of the wave. Like for the sea would be the distance between the top of the wave and the next top of the wave, this distance, okay? And in the sea you can find waves which are very far apart, or waves which are small and close to them. And the same with these electromagnetic waves. There are electromagnetic waves of all kind of length. The long ones are called radio waves. And if I would to give you 20 radios tuned to 20 different stations and tell you to turn them on, well, there will be a lot of chaos here, but we will all be sure that in this room, in this moment, there would be waves of all these different wavelengths, because when you tune a radio, you go to search for a certain wavelength. And then there are waves which are shorter. They are called microwaves, or they are called infrared. And then if I were to give you, I don't know, the night goggles of the army, where you can see the infrared radiation, you will discover that in this room, there's plenty of infrared and of microwave radiation. Then if you go even smaller, you reach a point which is very interesting, okay? A millimeter is like the distance between my fingers that you just barely see through. Divide this by 1,000 parts. It becomes really small, okay? And if you consider wavelength of a length that goes from 1/3 of this 1,000 part of a millimeter to 2/3 of this 1,000 part of a millimeter, this is light. So light is these waves that have this length in this very narrow, small range of values, very, very small, okay? And there is light in this room. There certainly is light, okay? There are lamps and light is reflected. Then you can go even to smaller, but I already made the point. My point is that we live in a world which is populated by all these electromagnetic waves of all kinds. And this one particular part, which is the one that has all this length, that is perceived by our eyes. And, sorry, I went backward. So, normally we see, because there are things like the lamps or the sun that generates all these waves that go around, and those waves have all the length of all the colors, because for each length is a different color. And that goes around and shines on things, and things reflect back. So for example, the sun shines on an apple with all the colors, and we see the apple red because from the apple we have only the waves of a certain wavelength, which is red, that go around. Okay, so I was saying we live in a world full of this natural and artificial wave that propagates everywhere. You can imagine all this bouncing off. And what does it happen that we see? How does it happen that we see? Well, there is an interesting analogy made for a very famous scientist, which is Richard Feynman, that was saying, imagine a pool, okay? Imagine a pool, and imagine that you don't see, okay? But you are an insect which is standing on the corner, on the right bottom corner of the pool, for example, there. You're just sitting on the water, one of these insects that stay on the water, and then someone jumps in, for example, a dog, okay? And this jump will produce waves, okay? And you don't see the dog, but you are there, and you perceive waves when they come to you, okay? And from the way they arrive, these waves, you reconstruct that, it's not a girl, it's a dog. And what kind of dog is it, and how far did it jump in the water? So this is what happens, that all these waves that populate the space, a fraction of this gets into these holes, which are the pupils of our eyes, it enters, and in some way, our eyes are this powerful tool that as the insect gets the waves and understands it's a dog, we get these waves and understand around us. So the next element is the eye. The eye, okay, this is a picture taken from the exhibit that we did. And what happens in the eye? In the eye there is something very important that I'm just jumping across this. It's a lens. In front of the eye there is a lens. Okay? And as you can see, there is this friend of mine who has his hand very strongly illuminated. There was a lamp underneath. And what does the lens do? The lens of our eye? Just make an image. You can see that there is an image on the back of the eye. Okay? So there is the real, can you see that? There is the hand. The real hand here. Then there is the lens. And then you see there is an image of the hand within the eye, on the bottom wall of the eye. And so the lens is this mechanism by which we kind of get a map inside. We get a map inside the eye, on our back wall of the eye, of what's outside. Okay? So if some light is coming from the top of the thumb, I'm sorry, this is not charging. Otherwise, it will turn off. Okay, now it's charging. If light is coming from the tip of the thumb, okay, there's the light illuminating the tip of my thumb, and you can all see the tip of my thumb. Why? Because light that comes here is sent in no direction. It enters in these holes that you all have, right? And in that, like the tip of the thumb there, light that enters is sent in one particular point, which is the tip of the thumb of the image. Okay, so we get an image inside of what was observed. Okay. For example, if you look at the letter A, we get an image inside. There would be a projection inside of the letter A. And the eyes are present in all the natural world, in a lot of parts of the natural world. There are very different solutions. And scientists have been studying the eyes of many kinds of animals, actually. And quite interestingly, the eyes, there are at least 10 times in the story of life on the planet Earth, the eyes have been invented independently. Meaning that eyes are almost always the same kind, but they kind of rose independently in the evolution of the animal species, many times. And this is quite interesting. And we see how animals would see, for example, this sea snail would see the letter A, it is on the bottom right, kind of fuzzy. But if an octopus looks at the letter A, sees fantastically, like we do. And his eye is independently evolved than ours, for example. Okay, so the eye is a really important mechanism that, is very effective in letting us enter in contact with reality. And the eye has two parts which are really, if you study them, really amazing. The lens I was saying before, but I will not talk about that because it's not so important for what I want to say, but I want to say that from the point of view of materials, how is the lens realized is a marvelous, combination of tricks, okay, that make this particular tissue transparent, elastic, that focus light is fantastic. But what I want to talk more is about this special skin that there is on the back of our eye. Because, we make an image, the letter A is there, but does this mean that we see? No, I mean, that's just an image on the back of our eye. That doesn't mean that we are seeing something by itself, right? Something else has to happen. That's not enough. So there is this particular skin on the back of our eye. And the skin is a very thin and special skin, which is made by 3 layers, as you can see there, 1, 2, 3 layers of cells. And these are very special cells. It is a piece of a brain, basically. Well, if you look at the embryo, the small child, as it develops, and the brain develops, and at a certain point, a little piece of the brain comes out and goes forward to form the retina of the eye. So one says the retina is a piece of the brain who came out to see how the world is moving. And in some sense it is. And scientists have studied this piece of brain that came out because it's very special, because it is of the same nature as brain, but it's simpler. So it's a very good place where to study the brain, to study the retina. And so it's made by 3 layers, and these 3 layers have 3 different meanings. one layer is a layer of cells that can perceive light, which means that there are these cones and rod cells, and again, doesn't matter, I mean, there are different kinds of cells. Some are sensitive just to light and dark, and some are sensitive to color. We have one which is sensitive to red, one kind which is sensitive to red, one kind which is sensitive to green, and one kind which is sensitive to blue. So we are saying this skin kind of gets excited. Some of the cell gets excited when there is light, period. And some when there is a red light, some when there's blue light, and some when it's green light. So we see these three basic colors, and as you know, in fact, with these three colors, we can build all the colors that we see. To see any color that we see, we can make the color that we see to a combination of red, blue, and green. So to show you this, I took my computer, I went down in the lab where there are many microscopes. You can see the letter A there, right? There's a small letter A on the side. Okay, so I took the computer and put it under the microscope, and the students were looking at me. Strange things to do, right? And so I can show you, if I enlarge this letter A, what I get something like this, more. Okay, this is a zoom, big zoom of what's on my computer, actually what's on my computer. And you can discover that we were seeing white, but actually the computer was shining a combination of blue, red, and green light, but to our perception that is white. Or you can do the same with the yellow, and you can discover the yellow is a combination of green and red, and purple, which is a combination of red and blue. Well, it doesn't really matter. And this is I mean, the details don't matter. It matters that we have these cells that are sensitive to colors and to light, okay? And these are our kids at our exhibit. There were 3 beams of light mixing, so they were playing with shadows. You can see that, depending on which beam you block, you get different colors. So, it was hard to get them to go away from it. Okay, so let me tell you a little more about this special skin, which is the retina, and then I will move to the next. But this is an important point. So there are 3 layers I was saying. Layer 1 is our cells that they get excited from light. What does it mean they get excited? They become electrical in some sense. They get electrified. And the more light there is, the more they get electrified. How does this happen? Well, it's all the fault of a small molecule that when light comes, changes shape. But this is another, okay, so this is a parenthesis. So there are these cells that get excited. Then there are the second layer, and the second layer, as you can see, are cells that touch one and the other of the first layer. They're connected to the first layer in a complicated way, and they do basically math. They add and subtract the electricity from the first layer and do operations, okay? And these operations are sent to the third layer down there, and then this layer is made of cells that take this result of the operation and send away pulses. So when the electrification is sent to the third layer, the cells of the third layer have a long, thin kind of hair that goes out. It's called axon. And this long, thin hair is something that goes away from the eye and it goes into the optical nerve and goes to the brain. So these are cells which have a tail. And when they receive this electrical excitation, they send pulses through their tails. So they send pulses out. So if you are kind of familiar with electronics by any chance, you can say that the first layer is like the pixel of your camera, of that camera. And we have 120 million of pixels in our eye, a lot. Then there is this layer which does compression. It's like a JPEG or MPEG compression. And it goes out to 1 megapixel, from 120 to 1. And there is a conversion from analog, such as light, to digital. So these are pulses. It's incredible, but it's like this. So what goes out from, sorry, okay. So if light comes in on the left, this is a graph of light coming in as a function of times. What comes out of these cells are pulses. And the stronger is the light, the more frequent are the pulses. Okay? All right, so what is happening? Something very important. that light is coming in and is converted to pulses. So the image is lost. It's not like there is a copy machine that takes, pictures and sends effects to the brain, right? It's some sense like that. It goes through a wire, like the fax goes through a wire. It's coded. The image is lost. What happens is that all these cells, put pulses out, electrical pulses, and some of the cells put pulses which are connected to the color. There's the yellow channel, so when it's yellow, there is pulses. When there is another color, there is not. Some of them, when there is contrast, a place where there is bright and dark, close to each other. And the cell which is close to where, for example, where in the image there is a contrast, if there is a contrast, shoots pulses. There are others that shoot only when the image is changing. There are others that shoot only when it's darkness. So it's not a simple image, it's a code. It's really a code. That is, the image is transformed into some, with some law in pulses, with a code. Okay? So the light comes in, goes to the skin, and then you have all these hairs from all these cells, 1 million, that go out, and that's called the optical nerve, and goes to the brain. And the optical nerve, you can see this is kind of scary. This is a small cut of the optical brain. Is made of fibers, 1 million fibers, that are going out of our eye and into our brain. And the normal rate of pulses that travel along this channel is about 100 million pulses per second. Okay? This is how the eye is communicating to the brain what's happening. Yes. Impressive and scary also a little. We'll get to the scary part in a little bit. I'm in fact here to present something that is going to scare a little, but because I think that inside this being scared there is an interesting thing that we have to look. And so, when I prepared this, I thought this was kind of similar to something we have seen in a movie, right? So this is the channel how the matrix moved the matrix. They pictured, when they put the plug in the brain, all the flux of informations that they are getting. And it's kind of like that, to be sincere. Okay, so that it goes, and the brain receives this enormous amount of spikes. What does the brain do? Okay, the brain, well, this gets a little obscure because we don't know exactly how the brain works. We know a few things, not all. We know that the brain is made, and this is my last technical transparency, then I will go to more general things. We know that the brain is made of neurons, the same cells that we saw in the retina. And neurons are cells that are branched, and each cell touches a lot of other cells, like 1,000 other cells. And depending on what the other cells around, let's take one, it has 1,000 other cells around. Some of them are excited, some of them are not excited. And the way it's wired to the cells is like it's doing basically some math. If that and that and that are excited and that and that and that are not, then I get excited. Otherwise, if there is another pattern, I don't. And it's like this. So the behavior of each cell depends on the behavior of the ones they're wired to. So you can, and there are 100 of billions of cells. So it's very complicated. You cannot really track what's going on. But you can do some things. People have learned that this is a topic which is incredibly studied. The two optical nerve, well, first of all, there is the right and the left, so they get mixed up. There is a lot of problem of connections there. But they are sent eventually in the back of our head. This colored part are the visual cortex, as it's called. They are visual areas. So it goes to areas that are divided typically in 5 parts. And we don't know exactly what's happening inside, but we know that the different parts do different jobs. There are parts that go recognize shapes. The part is more sensitive to the colors. The part is sensitive to motions. We know because there are people that unfortunately have problems. They maybe have been hit, or they have had a tumor, or they had some genetic misfunction. Maybe an area is not working. And so you understand what the area are for, and you have people that can understand what's in front of them only if it is static. As soon as it moves, it goes away, because there is one area that is to recognize only objects in motion, and an area which is to recognize only objects which are still. So there is something that's happening there, very complicated, super very complicated, made of these connections of neurons. And I could tell you more about this, but Basically, this is the picture. We don't need details. Okay. Well, one thing everybody would think is, okay, there is all this mechanism, but what we experience when we see something is a unified experience. Okay? And even if different parts of our brain, then the nerve, the coding, the decoding, one would think that you are getting different pieces that you have to put together, but we experience something which is totally unified. And why the experience is unified, neurologists don't know. Okay? They know the analysis, the analytical part is known, but how does it go together? It's kind of a mystery. And there was an artist that visited our exhibit that made this drawing on the left that reflected the complexity. So she was coming, there are, you know, she tried to say, you know, in an artistic way, to tell the story that I told you with flukes of people doing this and that, other, coding, decoding, there is a lot of passing, doing stuff, complicated. But when we look at something, like this Hopper painting, it's one shot. Okay, we get it all together. So the experience is unified, but I want to make sure that you get this scary thing, which is that this is interpreted. It is interpreted means that when you look at something, okay, we interpret what we see. In fact, here we can see a face or two faces. And actually, when we do that, this is a very old and known thing, when you do that and stare to that, you will see them oscillating. You will see the face and the vase. The face, vase, using. But this is more impressive. These are, on the left side, there is a big gray and two squares, okay? Two small squares. And the gray, the small squares is the same, left and right. Now look at the one below. There are two squares, and now the outside is changing shades of gray, right? It's light and dark. And the two gray dots have the same gray. But we see one dark, and on the other one we see it bright. But if you go there and measure, it's the same. And this stripe, horizontal on the right, is all the same gray. But we see dark on the right, and we see bright on the left. And it's not psychological. It's hardware. It's exactly those cells that when they see a contrast, they start shooting. So the brain gets these results and say, oh, there's this big contrast. So let's enhance. Let's put the black blacker and the white whiter so that we can see it better. Okay? So even if I tell you, it's not a trick that when you see it like playing cards, you say, ah, now I know. No, there's no way. I mean, the square on the left is going to be darker, whatever we think. Okay? Because this is how our eye is made. And it's even more impressive when you look at this, this is a chessboard, look at the square A and the square B. Now I can give it to you, you can try with PowerPoint. You can cut the square A and put it close to the square B, and they have the same shade of gray. But there's no way that we can see the same shade. And this is why the point I'm doing is that what we see is interpreted. One of the points, what we see is interpreted. I show you another one, and then I go to comments. So in 5 minutes I'll be close. Okay, this one, can you all see this? Maybe we can turn the light down, because this is, so I tell you a little. There is an image, you can see a castle with funny colors, okay? There is a dot, a black dot in the center, okay? Now you have to look at the bright dot for at least 30 seconds. Don't let your eye go away. Then I will change the image, and then the new image will have also a black dot in the same position. So you keep your eyes on that and answer a question I will make. Then I can go back and we can see it again. Okay, so I go down because otherwise I think I'm in between. So let's just look at this for a little longer. Don't let it go. The black dot. You watching it? Yes. Don't let it go. I'm going to change and let it go. Is it color or black and white?
It's color.
No, it's black and white. Oh. Now you move your eyes. Move your eyes. This is definitely black and white.
It goes back.
But there is no doubt you saw colors. If you didn't let the dot go, if you look at that for long enough, I switch, I see color, it's certain. It's certain because when you see look at the dot, you know, part of your cells, of your retina, that, for example, sees yellow, says yellow, 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 and there is something that's happening is that when we look at something, we call white the average of the colors we see. So we see only white, only yellow, yellow, yellow. Our brain and our retina start compensating and start calling gray or white the yellow. Okay, in fact, if you illuminate this hole with yellow lights, you can still see colors, which is incredible. But this is the same thing. So if you see yellow, 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 at a certain point your brain says, okay, what I'm seeing yellow, I call it gray. I call it gray. Okay, because this is my background color. Then I give to the brain the gray, the gray, and then the brain sees the opposite color. So instead of yellow, it sees blue. So I'm doing it once more, and the colors stay until the moment when you change the position of your eye. Then they go away. You can turn it back on. Okay, so I'm going to the end, but the end is the most important part for which I'm here to tell you the story. Two important conclusions. The first is, as I told you already, seeing is interpreting. Okay? When you look at this, until you then get that F, the street and fly there, you're kind of anxious and restless. It's bothering you. But when you see that there's an F, an L, and a Y, you see it, and aha.
Oh, I see it.
F, L, Y. F,
It's kind of perception because I don't see
Y,
it.
right? F, L, Y. So our seeing is interpreted. But the point is that this is a pure small piece that reflects how we are in general in life. We face reality trying to understand its meaning. Always. Seeing is just a small piece of this fact. There is not such a thing as a passive seeing. The moment we are engaged with reality through seeing, through vision, we are engaged in understanding what's the meaning of what's in front of us. There is no way. We continuously, when we look, we are seeking what it is, where it's there, where it's going. We're seeking the meaning of what's in front of us. Okay? For the vision, the meaning is what it is. How far it is, what's the color. I mean, we are seeing the description of this thing. And the fact that we can be tricked, okay, is exactly because we are built to understand. The way we are built is to understand. So we, the structure, we are made. I got a sentence that I couldn't terminate. The way we are structured is made to understand, so it's taking risks. It's adopting the best strategies to get the meaning of what's in front of us. So you can trick it. You know, you can trick it because it's focused to understand. But that's okay. That's part of, you know, the price you have to pay to be built to understand. Okay. This is the first point. And the second point is even more remarkable, I think. So yesterday, thinking of this, I went to, you know, the smartphone have all kinds of applications, right? So I got an application that I can click on a color. Told me navy blue. Told me the color. So I clicked on the blue of there on my screen. I clicked pointing at the blue, and this look at the color. It tells me the color. So the question is, does my smartphone see? It's a question that if you think about it, you get confused. So don't think, just answer. Here's my telephone. Who will say yes? Your telephone is seeing. Who says no? Your telephone is not seeing. And all the rest, I don't know what to do. No, I mean, our reaction is always, no, come on, the telephone is not seeing. It is made, you know, there is a detector on the side, there are electronics, and there is, you know, a memory where the colors are defined, and a display, and then the voice, okay? Okay, now, if you say that this does not see, imagine I'm a scientist of the future, not too far future, actually. Give me 30, 40 years more. And I can build a smartphone using organic pieces. I can take an eye. I can make the electronics. I don't do it with, you know, metal wires with electrons, which is what electronics. But I do it with neurons and ions. But these are, instead of electrons, you get ions. Instead of metal wires, you have this filament of neurons. And people are studying already circuits made of neurons. You can make circuits, right? And then you can, I'm saying, I can build this thing not made of electronical pieces, but made of organic pieces. Will be a strange, funny object that when I press, there is a small voice that says that, but it's all made of like animal pieces, let's say, okay, for example. Would that mean that it sees? And here it becomes complicated, right? Because I didn't do anything conceptually different. I just replaced the sensor with the eye, the wire with the neurons. What else? And so if it wasn't seeing before, it's not seeing now. I mean, let's be logical, okay? So it's not that the mechanism made of neurons it sees. I mean, neurons are made of molecules which are close to soap molecules. There are DNA, which is just a molecule, study DNA. There are ions, which are just, I mean, they are just normal stuff. I mean, complicated, but not, not magic, just molecules. Okay, step forward. Then I imagine to have here the head of someone. Just imagine, we are in the far future, okay? And I explain you exactly more than what I did today. We stay here 2 years because it's complicated. I explain you exactly everything that happens when this head looks at that door, okay? The color, the transparent mirror and everything, and how it goes, what goes to the optical nerve, how does it go in the brain, how the shape is constructed. All the I tell you all the mechanism. Would you be convinced that this head sees? No. The answer, the honest answer is no. And there is something very deep inside here, which is that I have been talking to you about a function, right? The function of the eye, the function of the nerve, the function of the brain. But there is a gap between the function and the experience. Of course, when I see the red of a shirt in front of me, then the photos go inside, excite the area, blah, blah, blah. All this is true. Every time I look at the chair, there is some mechanism inside me that is producing the analysis of the chair. But between the analysis, the circuits, the connections, and my experience, inside the experience of the chair, there is a gap. And the way to demonstrate this is something that all kids tell each other, which is, the Cartesio said officially for the first time, I think. How can you be convinced that when you see there, okay, we all call it blue, okay? But how can you convince that internal experience is the same for everybody of us? Maybe you see what I call red when you see blue, right? There is no way to know. We can see that the circuits are the same, but what is our experience of the color? We cannot tell. In fact, we cannot convince. Cartesio was saying, Descartes, sorry, was saying that if I am a man who sees the rainbow, normal. I get another man who sees the rainbow flipped, okay? And we stay there, we say, look at the same rainbow, but I see it like this, and he sees like that. There is no way, we can talk for the rest of our life, there is no way to explain to each other, to convince ourselves if the two rainbows are equal or different. Why? Because the function, which I have been explaining, is not the experience. There is a gap. And this is probably the most mysterious thing that we know in whole the natural environment world. And let me end with a couple of quotes that I think after this discussion are on this topic. This is from Huxley. How is it that anything so remarkable as a state of consciousness come about as a result of initiating nerve tissue is just as unaccountable as the appearance of the djinn when Aladdin rubs his lamp? Right, so she says, we are rubbing a piece of brain, and then we have the experience of red. How does this happen? In fact, you're never sure if your neighbor has an internal experience. Could be a zombie, right? Could be a machine. In fact, we always trick. I mean, when we go to the movie, have you seen artificial intelligence or even Star Trek, right? You see someone behaving as a person, and you get immediately convinced it has an internal world. But you can never be sure about that. In fact, there are millions of movies about this topic. And the second one is from a total hardcore atheist and materialist, which is Francis Crick, one of the two people who discovered the DNA, the structure of DNA. And the quote is from one of his last scientific papers. He was really an extremist, but he was intellectually honest. So he was saying the most difficult aspect of consciousness is the so-called hard problem of qualia. Qualia are this, which is the redness of red, the painfulness of pain, and so on. When you say I feel pain, I can say, okay, I know that this is what's happening inside your body, but what you feel really, I will never know. No one has produced any plausible explanation as to how the experience of the redness of red could arise from the action of the brain. We know everything about the red, where it goes, exactly everything of the circuit, as we know everything of the circuit that produces this voice that says red when I shine red. Okay, we know everything of this, but okay, doesn't tell us if my telephone is having an experience or my brain is having an experience. Okay, this is something that we say often when we close our presentation from the Eurisis Association. The point is that the scientific investigation of reality does not take away the mystery of things. Sometimes there is this kind of fight, right? Because you're thinking that knowing will take away, what's good in life. But actually, it changes. I mean, I hope that this story will kind of shift a little, no? Your worries and your feelings. So it changes, even dramatically it changes. But it does not take away. It gives a different angle. And I think more than,
So I have a question. What occurs in those people who are colorblind?
They have, for what I know, I think there are two kinds, actually, to be true. One thing is that I flashed at a certain moment, the reason why our cells get excited when there's light. There is a small molecule that when light comes, they change shape. Okay? And this starts a chain of events rather incredible. We move another molecule, there's a third molecule go away, that goes in a place, open a hole in the cell. I mean, but this molecule has a different sensitivity to the color depending on the environment it is in. Okay, so if you have a genetic, small kind of problem by which this environment is not produced correctly, you have not the variety of colors that you may have. But there is also a problem in perceiving colors down in the analysis. There's a book of Oliver Sacks, is a famous neuropathologist that told stories of a painter that got hit on the head and lost the sense of colors. So he was showing what happened to his painting. But anyway, so they are both things. Normally it's the first one I told you, but it could be. But I'm not an expert. I'm a physicist, not an ophthalmologist. So.
It looked to me like light is the presence of all colors, and is black the absence of all color?
Black is the absence of light. But to be really true, what you perceive as black is a result. I told you that there are some cells that are putting their pulses when there's dark. There are some cells whose job is to stay there, and when it's dark, they say, it's dark, it's dark, it's dark, it's dark, to your brain. Okay, so when it's really dark, there are these cells that are telling it's really, really dark. And then you say, oh, it's dark, right? So dark is produced by the absence of light. But the way it's communicated to our brain is through a particular channel to the optical nerve that says, the other cells are kind of quiet, they don't say there's light. And there are this one that says it's black, it's black. So yeah, but darkness is the absence of any colors or any light.
You cannot look at that and say there is no God. How can anybody know this and be an atheist?
Well, Francis Crick was.
Yeah, that's
And he
what
was
I
a pretty
wondered.
smart guy, yeah, absolutely.
How could it?
I honestly think that I go around telling this story because exactly what I was saying at the end. There is a lot of time you think that with the understanding of everything, there is no real mystery in life, but in the natural world. But this, I think, is the most sharp example of something that we definitely did not understand. And so I cannot, come from this to say that there is God, but I can certainly say that there is much more in the Word that we are not seeing and we're not understanding. That's for sure. Then, depends on your experience and on to say. I'm Catholic, but I would, not denying this. I'm just saying that from this I just can get a small, piece of the mystery that surrounds us. Yes.
You look in those mirrors in the